Today we have Vakilian with us. Vakilian is finishing up. He's in his third year as a research faculty here. It's been great to have him. He was actually in Tripod, an ideal postdoc before. And in addition to spending some time in other local tripod institutes as part of Ideal in Northwestern, he also, I think, before that, he was in MIT and in UIUC, so some of you have seen him there. And so Elias Vakilian has done work from an algorithmic perspective, but also many problems involving fairness and other social issues. Today he's going to talk to us, unfortunately not about meerkats, I think, but about streaming problems.
Yeah.
Looking forward to hearing.
Yes, thank you. Thank you, Nancy, for the introduction. Thanks everyone for coming. So today I'm going to talk about streaming algorithms, and in particular talking about streaming algorithms for connectivity augmentation problems, which I'll show you with. And it's joint work with Sezin, Michael Kapralov, and Sabita Ali. So what's the problem statement? In the connectivity augmentation problem, which we also call it referred KCAM, in the input we are receiving a k-1 edge connected graph G. And besides that, we are receiving a set of weighted links, I denoted by L, to distinguish it between edges in G. And we assume that the weights of the links L belongs to the set 0 to W. Okay, and then we want to output a minimum weight subset of links L prime, such that by adding L prime to the set of edges that we have in G, the resulting graph becomes K edge connected. Okay, just to make sure, we say a graph is K edge connected if there exists K edge disjoint paths between every pair of vertices. Okay, so you're starting with a K-1 edge connected, we're receiving a set of links, we want to add a minimum number of them so that the resulting one becomes K edge connected. Okay, so just to see an example, the black solid edges are a tree. This is a one connected graph, and we are receiving these basically options of the links, so the orange ones are the links, and we want to pick a minimum number of them such that the resulting graph becomes two edge connected. And maybe this one solution. If I pick the ones in red, then the resulting graph becomes two edge connected. Okay. So this is a very classical problem. For instance, the minimum spanning tree or tree augmentation problems are just special cases of this problem. If you set k equal to 1 or k equal to 2. And this is one. I'm mostly going to talk about connectivity augmentation problem, but we also have results for the more general problem, which called general network design problem, also known as SNDP problem. So in this problem, we are given a graph G, which has weight on its edges, and we also receiving a connectivity requirements R over the pair of vertices. And our goal here is to find a minimum weight subgraph of the input graph edge, such that for every pair of vertices in the graph, the subgraph edge that we have picked has at least R of SD edge disjoint paths between S and T. Okay. It's easy to see that just connectivity augmentation problem is a special case of this problem, and many other well-known problems are special cases of SNDP problems. Okay. For instance, to give an example, the K edge connect the spanning subgraph, where we have the requirement K between any pair of vertices, is a special case of SNDP problem. In that problem, if we set just all requirements equal to K for every pair. Okay, so what are the motivations? It's a very old problem, classic one, as motivation coming from wireless telecommunication network or transportation network, when we would like to add robustness and resilience to the underlying network, or we want to increase the robustness or resilience. And besides that, it's known to be very fundamental in TCS as well, and the combinatorial optimization problem. And so many of the advances in the combinatorial optimization approximation algorithm has happened for this problem, for when studying this problem. For instance, the primal dual has one of its earliest application for the SNDP problem, and its power actually becomes more apparent once people start analyzing it for SNDP and network design problem in general. And another one instance is iterative rounding method, which was actually developed for this problem. So it's known to be very fruitful in combinatorial optimization in terms of the techniques and ideas that have been developed. And besides, there has been many recent advancements on this tree augmentation problem and connectivity augmentation problem in just recent years, just for these very specific problems. It's just want to convince you that's a very fundamental theoretical problem and has also applications in network design. Okay, so let's see what's known for this problem in the offline setting. So for the general network design problem, we know it through approximation, and it's by iterative rounding approach introduced by Kamal Jain. And for the connectivity augmentation problem, actually it used to be, the two approximation used to be the best approximation for a while, but in recent years we know that these are the state of the art. For unweighted case, the best approximation is 1.393, and for the weighted case, it's almost 1.5. And we know that the problem is APX hard, so it's not possible to approximate it rather than some constant factor. Okay, so but as I'm going to talk about the streaming variants of this problem, let me first define what's the streaming model that I'm considering here. So I'm looking at the graph streaming model, and in this setting, we assume that basically in general in graph streaming, we assume graph edges arrive in a string, one by one, and in an arbitrary order. Okay, and then the goal is to use just a sublinear amount of space, not to store everything about the graph. And usually, we can just store order of n polylog in space, which is also known as semi-streaming. And then we would like just to solve the given graph problem. Okay, so we want to take one pass over the stream, use small amount of space, and then solve the problem. Okay, and so why it makes sense to study network design and streaming? As I mentioned, these days we are working with large-scale networks, and in many cases we would like to increase the reliability or resilience of the underlying network. So this is one model of things. And an interesting thing is that, unlike other graph problems like MST, matching, cut, sparsifiers, not much known is about this network design problem in streaming. Maybe the closest problem that has been studied in this streaming setting is the test connectivity, which is basically given a graph, we want to test what's the edge connectivity or vertex connectivity.
Yeah, sorry, either there's a typo or I don't understand something. So you said using sublinear space, and then you say big O of n times polylog n space.
Yeah, sublinear space in the number of edges. That's so the number of edges can be like n squared, and we want to use sublinear space.
But you're always allowed n polylog n.
Yeah. It's known that if you cannot do better than if you don't allow n, you cannot do anything interesting for most problems. That's basically what you have to do.
I guess what you don't make the decisions online, right? You output only at the end here?
Yeah.
Okay. So you kind of have to store in, if I understand correctly, just because the answer is of size? The answer is going to be of size
exactly. For many
or something like that.
Yeah, for many trivial reasons you have to pay at this end.
Connectivity also requires n, right? Like just answer the question if the graph is connected, it's also single process.
No n before n. Do you have
N?
Yeah.
Or just
Does the algorithm need to?
know the value of n.
Well, in a way, the k minus 1 edge connected graph is known to you, right?
Yeah.
That you're augmenting. So
Yeah, for that specific problem. For our problem, yeah, something like this. Yeah, but in general, yeah, I think for general graph problem, could be some instances that you don't know, and in advance you can just basically calibrate your guess as you see this. Okay, so that was the general graph streaming model. But let's see what it means for our problem, the connectivity augmentation problem. As just Samir mentioned, I mean, here we have more information. We already have a k minus 1 edge connected graph. So we can consider two different models. One is link arrival stream. So in this setting, we assume that the G, the k minus edge connected graph, is already given to us, and we don't count for the space of this graph G in the space complexity of the algorithm. So we assume that we have it. And basically, I mean, more formally, we assume that there's a link arrive in a stream one by one. So I mean, look back at the example that I described earlier. So we have this graph already in the memory, and then we receive the links one by one, like this. Okay, so on. And I mean, just some sort of justification why it's okay to assume that we have the k minus 1 edge connected graph, because I mean, it doesn't really need that much space. I mean, for instance, if you just look at the k edge connectivity certificate, then you need only order of nk space to store such graph. And even, I mean, if it's more careful and if you do some pre-processing, you can also store the information that you need from k minus 1 edge connected using a cactus representation that basically represent all min cuts using order of n space. So it's a reasonable assumption. But I mean, even if you're not happy with this, I mean, you can also think about another type of stream, which is a fully edge arrival stream. You assume everything arrives in the stream. So what it means that both edges of G and the links arrive in a stream in an arbitrary order. So basically, you receive edges of G. I mean, there are 0 weights or just maybe tagged that are already in the stream, already in the graph, and also you receive the links. It can be in an arbitrary order. And just want to make sure, I mean, since I described two problems, for link arrival only makes sense for the connectivity augmentation problem. For the general network design problem, since we receive the whole graph in the input, I mean, for this problem, only edge arrival makes sense. For general network design problem, whenever I talk about it, I'm referring to edge arrival streams.
Oh, yeah, you're only considering insertion only.
Yeah, that's it. I'll talk toward the very end, something. Okay, cool. Yeah, so these are the model. I want to make sure that's clear.
Just to make sure, the thing that happens online is storing this information, and you decide like what the solution is at the end, right?
Yeah,
This does not happen online.
Yeah, it's not online. It's a streaming. Okay. You don't need to make decision at the moment. Okay, so first let's see what are the results that we have, and then I'll describe some of them. So for K connectivity augmentation, we show that there is an algorithm in one path of streaming that achieve approximation to plus epsilon using order of n over epsilon times log n, and it's for link arrival model. And it's not actually possible to get a 2 minus epsilon approximation in better than omega of n squared space. So basically this is taught. And also, I mean, to get any approximation, you need omega of n space because it's just the size of the solution. Okay, so one just takeaway is that unlike the offline setting, that recent progress show that you can get better than 2 approximation. In a semi-streaming model, 2 approximation is actually the best that you can get. And for the other variants, a streaming model, edge arrival, we show that you can get, for any t, you can get O of t approximation in the space of nk plus n to the 1 plus 1 over t, and this is actually tight. Any order t approximation requires that many bits of space, nk plus n to the 1 plus 1 over t.
So earlier on you said that the weight of the link is between some 0 and L or something? Is that important?
0 to W. Yeah, that is important. Actually, one of our contribution is to make sure that the space doesn't depend on W. I mean, it's a trivial thing to get log W, but we can get rid of that. That's good. Okay, just for the edge arrival thing, I just want to mention an interesting special case. So consider the case that you first receive all links in the string and then receive all the edges of the graph. So in some sense, we would like to sparsify the set of links that we have so that later on, no matter what the graph we receive, we can augment it using that. So it's kind of some sort of summary or course set for this problem. So it's also interesting. Yeah.
I didn't follow your comment about the W. Like, what if I give you a history that is so large that you can't even read it? Like, how would you manage to run with space that is significantly smaller than log W?
Yeah, I mean, we can. It's fair to assume that log W is at this polynomial, right? Because we want to be polynomial in that. But we don't want to have the log W dependence on the space.
I see. So you're assuming log W is bounded polynomially.
Yeah, but we don't have log W in this space.
It's actually the number of words, right?
Yeah, it's number of words. Oh, okay, yes. It's not the number of bits; it's the number of words. So that's also captured. That you have to you have to store the weights. So, but yeah. Okay. Yeah, so that's what I meant. So receive the links and then maybe receive all edges of the graph just afterwards. Okay, just to go through the space complexity, note that the nk is basically the amount of space that we need to store. We need to store a k connectivity certificate for the graph.
What are we going to do for the interesting special case? Are we going to talk about results or?
Yeah, we have these general results, right?
So you're saying that this even works with. I see.
Yeah, I just want to emphasize that extreme case that you receive all links first and then see the graph afterwards. Yeah, so just to see why it makes sense. nk is basically the amount of space that you need from the G part, the edges in the graph G, so that you can store a k-edge connectivity certificate. And the n to the 1 plus 1 over t part is the amount of space that you need for the links. So basically, it's the number of links that you need to store. And if you look at it and look at this order t and n to the 1 plus 1 over t, it resembles the spanner trade-off. The distortion between the spanner and the space complexity of the spanner. And in fact, one of the takeaway here is that we show that the spanner is the sparsifier, is the right sparsifier for connectivity augmentation problem. And that's one interesting observation.
Sorry, can you elaborate on the last part? What do you mean by spanner specifier for the connectivity?
So that if you want to solve it in this setting of edge arrival, that links may come earlier, the right thing to do is just to have a spanner over the links. And this is the best thing that you can do. That's what it is. And this is also basically the tight tray. Okay. So first, let's see. So as this suggests, it means that we first need to see what we can do for spanners in the string. And spanner, it's a very well studied problem in streaming. And for instance, we know for the unweighted case, it's easy to come up with order t spanner using order of n to the 1 plus 1 over t many edges. But for the weighted case, it's a bit different. It's still easy to get using existing method and do some standard bucketing method to get order t spanner using n to the 1 plus 1 over t times log w edges. So this is the number of edges. Okay, yes, back to point. So if we just follow this simple approach, we need that many edges for the weighted spanner. But we would like to get rid of this log. Okay, and this is what we show. We show that for the weighted spanner in one pass, we can have an order t distortion, and the space that we need is O tilde of n plus 1 over t. And I mean, that trivially, I mean, in terms of bits, that's the best we can hope for, and it's the edge hierarchical setting, of course. Okay. Okay, so I'll talk about these results more. Let me just also mention what our results for connectivity augmentation problem imply for the network design problems. So using the result for connectivity augmentation problem, we can show that there exists a single pass streaming algorithm with approximation order t log k that uses a space k times n to the 1 plus 1 over t. And from the lower bound part, we also know that to get order t approximation, we need at least omega of n to the 1 plus 1 over t. So yes, there is some gap, but we'll also talk about it later. How we can actually close the gap, or what's the status there. And also for KEC CSS, edge connect the spanning subgraph, we show that, I mean, you can use the result for SNDP as it's a special case of SNDP, but besides, I mean, we also have a k-pass streaming algorithm achieving log k approximation in the space nk log k. Okay. So that was basically some introduction and the results that we have, and let me give some overview of the algorithms for these problems. Okay, so let's start with the weighted spanner problem. So what we know about this problem? So in the input, we are receiving an edge-weighted graph G, where the weights belong to 1 to W. And we're also receiving a distortion parameter T, and we would like to return a subgraph edge of T such that edge is a T spanner, meaning that for every pair of vertices U and V, the distance of U and V in edge is less than T times the distance of U and V in the original graph G. Okay, so what's the simple algorithm? So let's consider the unweighted graph. So for unweighted graph, I mean, there's a very simple greedy algorithm. So we start with an empty graph H, and then just start processing edges one by one. And for each edge E that we receive, we check if adding E does form a cycle of lengths less than order t. I mean, I say order t because there's some constant t here that matters, but let's say if it constructs order t cycle, and if it doesn't, we just add it to this one. Otherwise, we just ignore it. If it's going to make a short cycle, then it means that we don't need to store it. Otherwise, yeah, we'll keep it. Okay, so it's very simple algorithm. And it's also, besides being simple, it's also streaming friendly. You can easily implement it in a streaming, right? I mean, you can just run this greedy algorithm in the streaming set easily. And we get basically what you want. We get order T spanner, and the space that we need is n to the 1 plus 1 over t. Okay, so now what's the simple thing that we can do so that it makes for weighted case? The simple idea here is that to partition the edges into log W classes, such that the weights inside each class differ only by a constant factor. There's a simple doubling idea, right? And then we can maintain an O of T spanner for each weight class separately. Okay, so we have a separate O of T spanner in each weight class, and at the end we just merge all of them. Okay, so this is also very simple, and we can just show that it's still O of T spanner. We're just losing a constant factor, extra constant factor because of this bucketing idea. And the space complexity but increased by a log W factor, because this is the number of weight class that we have. So now Yeah, now the question is if we can get rid of this log W dependence. Okay, so we had to pay this log W, as I mentioned, because the simplest idea is just to have these log W partitions and so on. But we show that we can do something more clever, which we call even odd bucketing, and get rid of this dependence. And how it works as follows. So now instead of looking at partitions that differ by a constant factor, we are partitioning the weight into buckets that differ by a factor of n almost. Okay, so it's like n to the I minus 2 and n to the I minus 1. Call it the I minus 2 bucket, the I minus 2, n to the I minus 1 to n to the I. This interval is bucket the I minus 1 and so on. Okay, so all differ by n. And why it's useful? Because now we have this property. If I look at any, if I look at an edge here in BI, and I know that there exists some path using the edges of BI minus 2 and smaller, then for sure the weight of the alternative path is smaller than the weight of edge in BI. Okay, because the length of any simple path is at most n, and all edges in BI minus 2 and smaller, or at least by a factor of n smaller than the weight of any edge in BI. Okay, so that's the key property that we will get from this bucketing. Okay, and in particular, what we are going to do, we are going to separately construct a spanner for even buckets and odd buckets. Okay, so means that first I look at, let's say, call them the even buckets. I construct a spanner on them, and also I construct a spanner for the odd buckets, and then at the end I merge them. But this nice property that we have, it allows us to do something more clever for even and odd buckets, and can save a factor of 1. We'll see shortly how it can happen. Okay, so that's basically the two steps I'm going to follow. Consider even and odd buckets separately, and then try to combine the T spanner for these two buckets at the very end. So let's consider the algorithm. So for any edge UV in BI, as I mentioned, if there exists a UV path in even buckets of BI minus 2 or smaller, then we don't need to keep UV in the spanner. Okay, so that's what I mentioned also earlier, because for sure that path has a lower weight. And now we only need to deal with the edges of BI that are between different connected components of the graph constructed using the edges in BI minus 2 and smaller. Okay, so what it means, so let's these be the connected components of the graph G using the edges in BI minus 2 and smaller. Okay. Then I don't need for sure to keep any edges that is like have both its endpoint in the same connected components, and also for any edge connecting two different components, if I have another edge with a lower weight, I can also get rid of this red edge. Okay, so basically I only need to keep a simple graph over the connected components. In particular, you can think of contracting this connected component and just try to store edges of BI in this contracted graph. I will see actually we only need to store a spanner of BI over these contracted vertices. So that's basically very high level. And the main thing is that if there are case supernodes or after the contracting these connected components, then the amount of space that we need for of the spanner is O tilde of x to the 1 plus 1 over t. And that's basically the amount of edges that we need to store from each bucket BI. Basically, I mean to be more accurate, since BI has a range of the weight difference in each bucket is order of n, if we want to use this, we want to store the spanner structure, we need to do this simple weight of the spanner idea that I mentioned, that partition into the log of W, where now the W for inside each bucket BI becomes n, because the difference is n, so it becomes log n. So basically for each bucket BI, we are storing x to the 1 plus 1 over t times log n now. So we get rid of the log W inside each BI. And the cool thing is that we can show that if BI picking some edges, then the connected component has to decrease in some sense by the number of edges that the BI is picking. Okay, so we'll have some progress depending on the amount of space that BI is going to use. So that's some technicality here, but if you think, you can just write the formula and everything and show that basically overall, the amount of space that we need, or basically the number of edges, would be order of n to the 1 plus 1 over t. Okay. So yeah, this is, I hide some of the technicalities, but this is the high level thing that we can that we do, and basically this is the final bound that we get. Okay, so I show, for even buckets, we get these bounds, so we can construct a spanner of that size, and we repeat the same thing for the odd bucket and get the same result. And so in total, we have just order of n to the 1 plus 1 over t, or tilde of n to the 1 plus 1 over t. Okay, so but we should be careful, because in the streaming, it's not as simple as I mentioned, because edges may come in any order, and once they arrive, once an edge arrives, we may need to change too many things into too many buckets, right? Because just adding an edge, if you look at this picture, adding an edge, for instance, may cause some connected component to collapse and so on. So it's a bit, it requires some more work to take care of that. And we can show that, this is possible. We really don't need to maintain the connected component and everything, or supernodes, or the contraction. What we really need is to have the graph H and being able to compute the connected component at any point. And this is possible. So once we have the set of edges that we have stored so far, we can always decide, we can figure out what are the connected component for each bucket BI minus 2, as I described. So this part is not that difficult. The other thing is that what we should be careful about is that whenever we add an edge to one of the spanner, we should go through all heavier buckets and sparsify them. Okay, and it's still okay. It won't increase the space complexity. It requires some time to just go over and just fix everything, but in terms of space complexity, it doesn't add anything.
Intuitively, I feel like I don't understand why we benefit from doing this separately on the even and odd buckets. Like, why don't we just kind of run the even bucket procedure on all of the buckets at once?
Yeah, because I want this property that I want to be sure that when I'm processing an edge here, all edges in the lower buckets are differ by a factor of n. But if you consider the edge here, it may be very close to this, but it's just constant factor. So it doesn't suffice. Yeah, but it's very good.
I guess a follow-up to that question I would have is, why don't we just if we guess with a larger gap, then there has to be something we pay for, right? Because otherwise, why don't we guess with into the 100 or 2 to the n? So, yeah, what is that trade-off factor in?
And to the I guess that would. It would be the log of that will also appear. That's the time. But for n to the 100, it would be just in constant.
Just the same.
That could be okay.
Super polynomial will be.
Yeah.
I see.
But you cannot make it too long. So yeah, that was for the weighted spanner, and let's see what we can do for the K-cap. For the edge arrival stream, actually just the algorithms immediately follow from the algorithm that I described for weighted spanner, because this is what we are really doing. For the links, we are storing a K connectivity certificates. For the edges, we are storing a K connectivity certificates. And for the links, we just keep off T spanner. Okay. But for link arrival stream, it's a bit different because we cannot just use the spanner as a black box. But we are using the same idea, even out bucketing, but we need now to deal with a different type of structure and objects coming from this connectivity augmentation. Just let me very briefly tell some of the differences. So, I want to show the two approximation algorithm for link arrival stream. So, consider connectivity augmentation problem, and it was observed in approximation algorithm literature by some Asian school authors that basically to solve connectivity augmentation, we only need to solve the cactus augmentation. As I mentioned, cactus is a compact representation of all minkans. And it's known that, if we want to, from even to odd, is like tree augmentation, from odd to even is like a cactus augmentation. So in general, it's like a cactus. And it was actually recently observed that, and that was basically one of the main technical parts for the recent progress in connectivity augmentation problem in offline setting, that the cactus augmentation can actually be reduced to cycle augmentation. So then that's a much simpler object now. So we are given a cycle, and we want to just augment its connectivity to 3, let's say. And yeah, this is, for instance, observing this toolbar. So first, let's see what, if we are okay with losing a log factor, what's the overall idea. So this is what we can do for the cycle augmentation. So we have a cycle, we receive a set of links, we want to pick a subset of them such that the resulting graph becomes 3 edge connected. And what matters here is that we want to make sure that if I look at any two cuts, then there exists a links that I have picked such that crossing this the cut produced by these two edges. And this is basic. So for example, in this example, if I remove these two edges, I have to have some edge links crossing. And this, for instance, one of them. Okay. So to show basically how we can solve it, this is an approach that was known before. So we pick an arbitrary root node 1. And then for any vertex V, we only pick two of its edges closest to these root nodes. So one from this side and one from this side. So basically we are picking 2 edges per vertex. And it's kind of easy to show that, it's always, there are always enough for basically covering all these 2 cuts that I described. And the nice thing is that the total number of edges that we need to keep is order of n now. We only need 2 edges per vertices. Okay. Yeah, this is interesting observation, and yeah, I unfortunately don't have time to go over it, but.
So you're kind of assuming that these edges have roughly the same weight because they're one
yeah,
group
yeah, exactly. That's actually for unweighted. I'm describing it for unweighted, but simple adjustment for the weighted cases again to partition into log W. But as I mentioned, we're also doing even odd bucketing so that we can get rid of the log W. But I want just to give an idea how the underlying algorithm works.
Are the reductions from connectivity to cactus and cycle augmentation approximation preserving?
Yeah, this is for sure. Yeah. They're all.
So we can just think about cycle augmentation.
Yeah, exactly. They're all approximations. Okay. So yeah, so this is what I mentioned for simple adjustment using log W for the weighted case. But if you want to be more careful, we can also do even odd bucketing, get rid of the log W. But there are some challenges because now the components that we want to work with is not connected component anymore. We have to work with the 3-edge connected component. So it's a bit more messy. And then once we shrink the components, then the problem is not anymore cycle augmentation, but still have some nice structure that we can exploit. And so I don't want to go through them. So let's also describe a little bit what you can do for general network design problem. So for k-edge connected spanning subgraph, one observation is that we can, once we have the algorithm for connectivity augmentation problem, we can just use the augmentation framework from Williamson et al. And this is basically means that we try to increase the connectivity one by one in each pass until we get to k. So in first pass, I just make a connected, make a tree, and then in the second pass, I can augment the connectivity of the tree to 2 and so on. And just by the algorithm I described, it's a very simple extension. In k pass, we can use nk plus n log in the space, and the trivial approximation bound would be order of k. But if we are more careful, we can show that it's actually order of log k. And the reason is that because the integrality gap of the L relaxation for augmentation problem is constant, is 2. And we can show that the problem that we need to solve in the L phase of this connectivity augmentation problem has optimal fractional solution whose cost is less than the optimum cost of k-edge connected spanning subgraph over L. So this saves over this harmonic type of series. Yeah, this is some technicalities, but this can be done. And for general SNDP problem, in this work we show that we can actually, similar to the spanner idea, now we can have a collection of k-spanner-like structure, and that could be enough to solve SNDP. And then we use the augmentation framework to analyze the approximation, but this time it's in the reverse. So it's by another work by Gomez, and it's Williamson, Hardosh. So this is also known in the approximation literature, and this will allow us to show that in one pass we can, using order of k n to the 1 plus 1 over t space, we can achieve order of t log k approximation, where the log k approximation, again, coming from this reverse augmentation framework. Okay. So let me summarize the talk, and also at the end I would also like to talk about some of my other research, since it's a research at TTIC talk, to see what else I'm working on. So yeah, so summary, I showed, network design in the streaming, yeah, and its connection to the weighted spanner. Maybe that's one of the main takeaway of this talk. And this is the result that we have. I talk about some of them, but I didn't talk about the Steiner tree augmentation problem as well, but you can find them in the paper. So one question, as I mentioned, and actually I mentioned it the last time I gave this talk in summer in assignments, that if you can close the gap for SNDP and KECSS, and actually since then, in the work with Chekory, Jane, and Sabita, we actually come up with a generic framework that can be used to achieve tight bound for ECSNDP, and also providing results for vertex connectivity variance, and also could be extended to non-uniform network design. So it's kind of interesting result. Hopefully will be out soon. Another interesting question is to look at the result for unweighted k-cap. So what I described was for the weighted cap. For the weighted cap, these are the bounds are tight, but for unweighted, the problem is a bit different. Still from the upper bound, 2 plus epsilon approximation is the best we know. But for the lower one, we only know that we cannot do better than 1.4 almost approximation. So what's the right answer? That's an interesting question. And it's also an interesting question to study the problem in dynamic stream. As I guess Chen, you asked, yeah? We have some ideas, but yeah, it's interesting questions. Okay, so let me also now go to other research this direction I am interested about. So,
quick
yeah,
question.
sure.
On the bottom row, you think that you're claiming 2 approximation, or what is the bound you're claiming for KECSS? For the bottom row. Yeah.
The approximation in log K.
No, but you said the new result gives you a better bound.
Oh, this one? No, for that, I mean, we get order. Okay, so for that we get.
Because offline we can do 2 there, right?
Yeah, we get rid of this log K. Yeah, we don't actually have a result in this
Okay.
for K pass. We only have result in 1 pass. Yeah. Or K pass is still, I mean, that's the thing. But for 1 pass we get better. So basically getting rid of this log K and also saving a bit on the strings. Okay, so let me also briefly talk about them. So another direction that I'm interested in is basically looking at algorithm design in the age of AI. And what I mean by that is that, so 2 direction is like, so basically is looking at the success of the AI, how can we use them as an algorithm designer to develop better algorithm. And this is what I call learning augmented algorithm that I have worked in the past few years. And the other direction is basically how we can, although I mean the AI approaches are very powerful, very successful, but they have also raised many ethical and societal concerns. Now the question is how we can design algorithms that treat individuals more fairly. It would be problem dependent. Okay, so let me start with this learning augmented algorithm. So here the idea is to use ML component in classical algorithm to improve the performance beyond the worst case guarantees. And it has been very popular recently, and there's a repository that collecting all recent work on this topic. Algorithm with prediction. If you're interested, you can check it out. But here is the high-level description. So we would like to design algorithms that have better performance when the input has some nice patterns. And this is the part basically machine learnings are very good at detecting. And the way we abstract out exploiting the pattern in the data is via an access to a machine learning oracle. So we assume that the algorithm has access to a learning oracle that provide some sort of extra information about the input to the output. But on the other hand, we don't want to sacrifice the worst case guarantee that we already know. So we would like to make sure that no matter how that oracle works, even if the oracle is adversarial, we can still be comparable to the existing worst case guarantee. Okay, and basically, as I mentioned, the first part is a place where machine learning are very good at, and the second part is the place that the classical algorithms are usually care about and are very good at. And in the learning augmented algorithm, it basically means we want to have the best of both worlds. So have both adaptability to the pattern and at the same time providing worst case guarantees. So I have worked a lot on this area, mostly in the streaming setting and combinatorial optimization. And I would be happy to talk about it if you are interested in. So the other aspect is just algorithmic fairness. I'll quickly tell something about that. So in classical algorithm design, usually the objective is to optimize the accuracy, runtime, or space complexity, for instance, as in the streaming algorithm I described. We try to just optimize the space complexity. But in reality, I mean, the algorithm may have very different impacts on individuals that are working or interacting with it. So, and then people have come up with the different notions to capture the way that the user maybe interact with the algorithm. And some of them are statistical parity, equal opportunity, and so on. So there are some other notions that we may want to also satisfy as an algorithm designer to capture these fairness issues. And in particular, a large part of my research was on studying the fairness of clustering. And why it requires special attention because clustering is a widely used method and it has many different applications. So for instance, it can be used as a partitioning methods, like partitioning individual and assigning benefit to them differently. Or it can be used as a means of data summarization, like returning the centers, for instance, in the clustering as a summary of the data sets. Or it can be used, if we can consider it as a facility location type problem, and we want to capture the access of users to the facility that we opened. Okay. And I mean, because of this wide application, there has been a wide set of notions of fairness for clustering. I have worked on many of them. And actually, I recently gave a talk at the workshop by Ideals at Northwestern. So if you're interested, I would be happy to talk more about that. And also maybe the videos are available, I'm not sure. But yeah, that's another thing that I'm very interested in, the fairness of algorithms and clustering. And more general, I mean, fairness of data summarization. That's a more recent paradigm that I'm working on. Because I don't have much time, so let me get back to the final slides from the streaming algorithm. And thank you, and let's see if you have any questions.
Questions for me?
I'll ask a question. So in the case of the learning augmented algorithms, don't the original, if you have worst case guarantees already, doesn't that just directly apply to anything that's augmented by some learning pattern recognition?
It depends. Sometimes you cannot do that, right? I mean, for instance, consider the online setting. So you have to decide at any point whether to do something or not. So either you have to follow the worst case guarantee or follow the prediction that want to hint you to do something completely different. So you have to somehow figure out how to.
I see. I was thinking of.
But in some cases you can. If you can run this in parallel, sometimes you can just return the best. Sure.
Yeah. So for a lower bound of spanner, it follows from a reduction from cap or it's separate? To or from?
So this one?
Yeah.
Oh no, this
No, yeah.
Oh, it is all from just the Erdős conjecture.
No, but Erdős conjecture is conjecture. Now you're saying you have unconditional lower bound.
No, but what we have, I mean, if you don't care about the constant, we know that there exists some lower bound. The exact, yeah, the 2 t-1 and n to the 1 plus 1 over t is conjecture, but order t and that is
I see. Because I was wondering if you have another proof for that.
No.
Then maybe you can say something about
Erdős
Girth conjecture. Yeah.
Not at this
Very
point.
fancy. Yeah. So okay. Yeah.
Good point.